Mass in infrared spectrometry and proton and carbon-13 in MR. I'm Stephanie Heron.
I'm Seth Eddington.
And I'm R.D. Aidini.
So we will start with mass spectrometry. We start by finding the M+ peak. Our graph does not show it. Usually it should be the rightmost peak. We calculated it by adding the molar masses of each atom in our formula, which gave us 116. Now for the base peak. We look for the tallest peak in the graph, which occurs at 43. The degrees of unsaturation can be calculated with the formula here. Using our formula, we get a degree of unsaturation of 1. This means we either have one ring or one double bond in an alkane. This is all we can learn from mass spectrometry. If any further help is needed, it can be found on this helpful graph from Compound Chem.
We have this figure here that has wave number over transmittance, and we're typically going to have 5 zones which each has its own functional groups associated with it. So zone 1 starts from 3700 to 3200, so we're going to go from here to here, and it's going to be zone 1. Zone 2 is from 3200, starting there, to about 2700, so it's going to be around here. Zone 3 is from 2300 to 2000. Zone 4 is from 1850. It's about 1650, so around here. Zone 4, and then Zone 5 is from 1680. It's a little loud at the library today. About 1620. It's going to be Zone 5. So now we have to look at peaks and see if each zone has a peak associated with it. And as we can see in Zone 1, we do not have any peaks. So we will not have functional groups such as alcohols present in our structure. Zone 2, we do notice that we have a peak. And this is typically going to mean that we have a carbon to carbon sp3 bond. Zone 3, we don't have anything. And here we would typically find carbon-to-carbon triple bonds or nitriles and things of that nature, but evidently we don't have anything here. So in Zone 4, we notice that we do have another peak. And in Zone 4, we're gonna find esters, aldehydes, and things of that nature. Zone 5, we notice that we don't have anything as well. And then after Zone 5, this area is known as the fingerprint region, and we disregard this region completely as it is not beneficial towards our structure. Spectroscopy, which shows all the functional groups that can be observed in each specific zone.
Hydrogen 12, oxygen 6. So we can start by looking at the integration numbers for our graph here. So starting on the far right, we have an integration number for this peak of 6. Looking left, we have an integration of 3 for this large peak, and the next 2 peaks on the left look to be split, which means that some of our hydrogens in our structure are going to be split up into 2 groups. This has an integration number of 2. So now we can start to attempt to draw our structure. So we do know we have a carbon to oxygen double bond, and we know that we do not have any alcohols, so there cannot be any carboxylic acids or anything of that nature. So we are looking at, more than likely, having an ester. So we'll start by drawing our ester. Here's our double bond, oxygen, 1 carbon, 2 carbon, there's that, and there's our full ester. So, moving on from that, we do know that we have a singlet, which I will put up on, we'll show you where. We have a singlet here, meaning we more than likely have a CH3 functional group, a methyl functional group. So we're going to add on the rest of our carbons now. We have a total of 6 carbons, and right now we have 1 here and 1 here. So we need 4 more. So 2, 3, 4. But we have a splitting of our but we do know we have the splitting of some of our hydrogens, so that would mean that we need to also have another carbon right here. So now we have a total of 6 carbons, 1 here, 2, 3, 4, 5, 6. So we have satisfied our need for 2 oxygens and our 6 carbons, but let's make sure that we have enough hydrogens in our structure. So we have 1, 2, 3 hydrogens here. We have none in this section because all 4 bonds are used to the carbon. None on the oxygens. We have 2 here, 1, 2. 1 here, since only 3 bonds are made. And then we have 3 on each of these. 2 and 3. So, in total, we should have 12. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've satisfied all of the atoms in our molecule now. Now we can identify if we have the correct structure itself by looking at the integration numbers and our proton NMR chart for number of peaks and such. So for this group, we have 1 hydrogen that we can look at, and we go and look at the adjacent carbon to it and count how many hydrogens are on there. So as we can see, this is our adjacent carbon. There are no hydrogens, so that would be 0. Now, with this, we know that with the n+1 rule, we have 0 from this carbon plus our 1 that we were looking at, which adds up to 1. So we should have 1 peak. Well, we have 1 peak right here. So this was our CH3 functional group, and it has an integration number of 3, as we discussed earlier, which are counting for each of these 3 hydrogens that are in the environment. 1, 2, 3. So this goes with this peak. We will draw that arrow in there real quick. All right. Moving on to the next. We have a septet right here. We have our singlet right here. And then these 2 are slightly different. We'll see why in just a moment. So we have our integration number of 2 here. So we know that it is more than likely going to be an indicator of this carbon here with 2 hydrogens in this environment. So as we talked about earlier, this looked like it was split, so our hydrogens may have been split as well. Starting here, if we go to the next adjacent carbon, it breaks off into 2 groups, which are these 3 hydrogens there and here, which means that this is our group right here. Moving, and we're going to put that arrow right there. Now lastly, we have our 1 more integration number of 6, which are these in total. All of these have an integration number of 6. That makes sense. And then to the adjacent carbon, there's 1 hydrogen. N+1 means 1 + 1 = 2. We have 2 peaks over here, and that is our final peak. So we know that we do in fact have the correct structure, and we can move on to carbon-13 NMR. This is a chemical shift guide to proton NMR. Numbering our peaks. So here on the far right, 1, 2, 3, 4, and 5. So we'll draw our structure. There we go, there's our structure, poorly drawn. Now, we know that our 1 and 2 peaks, the farthest to the right of the graph, are going to be the closest ones near the oxygen, which is the most electronegative atom. So, number 1 being double bonded to oxygen right here. So that is our number 1 value. Number 2 is going to be the next one closest to the oxygen, which is right here. So now we go on to 3, which is going to be the one where it actually ends up splitting off into the 2 separate carbons over on the far left. Number 4 is going to be here on the far right. And then lastly, remember we have the one environment that's split in 2, so this carbon here is going to be 5, as well as this carbon here. And that is how we do carbon-13 NMR for our molecule. Thank you so much for watching, and you have a good day. Quick.